In the last couple lessons to close up this series of training or training lessons for ANSYS, I'm gonna do um, transient or time-dependent analysis again, and this time I'm gonna apply harmonic loading on a sample. So in lesson 18, we studied impulse loading, which was basically a load applied to a sample at a very short period of time. And in lesson 19, we studied a time-dependent load of ft was equal to amplitude times sine pi over 4 times t. This time in lesson 20, we're going to study a load which is constant, or which is not constant, but it's stepped, like step loading, like this, at different frequencies. So let's say this uh, total load is constant at 1,000 newtons, but frequencies range from 0 to, let's say, 50 hertz. So we're going to study how our model behaves at different frequencies while we're given a step load of 1,000 newtons for that frequency. So it's again another type of time-dependent analysis and ANSYS. And this time the other thing I want to teach is how to define stress concentration um, during meshing. So if you remember from previous lessons, if I had a line like this, I could ask ANSYS to divide it into a certain number of segments which could have equal lengths, or I could also divide this line into segments in a manner that as we proceed from end to the beginning of this line, the uh, the size of these segments increased. The other thing I wanted that is interesting in meshing a sample is, let's say we have a point which is a stress concentration point for us in this model. Imagine a crack in a sample. So I want to show you how you can define a stress concentration point on your model. So basically the analysis or the simulation I'm going to do will be very similar to fracture mechanics concept. So uh, I'm going to define this model. Let's say we have a sample which is a 3D, and we have a crack right in the middle. So let's say this length is it's called 2W, and this length is usually called 2A, which is the length of the crack. And then we have a height in here from the plane of the crack um, to both ends, and it's usually at the center of this it should be here, center of this model. So basically this area that I'm gonna encircle with red has some singularity, because this is actually an open surface, which is and is it's a sort of a separation of the material of the atomic structure on this surface. And so we're going to study this case. Again, there is a sort of symmetry found in here. So if I say here and this line are showing me a symmetry, so I can model this quarter of this sample and have I can define 5 key points, and this is going to be here. So I have 5 key points, and I can have lines that are connected from each key point to other key point. And this point I have stress concentration, and this line and this line are going to be symmetrical points because I have the same half on this part of the line. Also, I have the same path on this part of the line, but I don't have to define symmetry in here because as I define this symmetry, the singularity is going to be applied to both halves of the sample. And then I'm going to also apply a pressure of 1000 Newton millimeters, and then define the frequency of 0 to 50 Hertz for this analysis and run this harmonic, I'm going to call it harmonic simulation in ANSYS. Like the previous simulations, the material is going to be steel with the elasticity of 200 gigapascals and Poisson's ratio of 0.3, and yeah, we're going to go from here. So let's go to ANSYS and run the simulation. Okay, and ANSYS, the first thing I want to do is to click structural from the preferences window and come to preprocessor, and again select my element to be solid 8 node 183 plane 183 element here, and in the options window I'm going to pick plane strain because plane strain is usually more conservative in results than plane stress. So click OK and close this window, come to material properties and define the material properties for my model. Steel with 200 gigapascals elasticity and 0.3 for Poisson's ratio, and click OK and come to modeling and create the key points that I need. First one is at 0 and 0, and I'm going to give a length of 1 millimeter to my crack, and then 10 to the width, and then go 10 in height, and eventually get back to x of 0. So I have defined 5 key points. Now I can go to lines, pick lines, straight lines from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and for this one I want to pick from 5 to 1 to have the end point at this location, and click cancel. And our areas arbitrary by lines, and I'm going to pick all the 5 lines that I made and click OK. So the area is generated. Now I have to come to meshing. The first thing is I want to do size control, manual size on lines, and pick this line first and say I want to divide that by, let's say, 20 segments. Any segment is 0.2, has a spacing ratio of 0.2. Click apply. Then I want to divide this line and this line by, let's say, 15 without any spacing ratio. Okay, so far everything was similar to what we had done before, but then for the stress concentration point of here, I would come to concentrate key points, create, pick this key point and click OK. So the key point of concentration is key point number 2. The radius, I want to pick 1/8, which is 1/8 of the crack length, and then for the second row I'm going to pick let's say 6/8, which is 3.4, makes it a little bit bigger in the radius, and I want to have 8 elements around this point. Click OK, and if I do the meshing in area free, you will see this. Let me zoom in this point. So I have 1, 2, 3, 4, 5, 6, 7, 8 elements surrounding this key stress concentration point. And this is the first radius, and this is the second radius. So you see how it's generated. Zoom out, and then it's time to apply my loads. So I come to analysis type, new analysis, and this time I'm going to pick harmonic. Okay. And then I come to analysis options, and I want to pick full solution method, and I'm picking real plus imaginary for DOF printout format. Um, the real part will be the amplitude of the uh, uh, time dependent or frequency dependent loading that I'm applying, and imaginary part will be the frequency or the phase of the complex number that defines the load which is applied to this surface or this uh, area of the material. So I'm going to pick that one and click OK. In this next window, I'm going to stay or stick with the defaults and click OK. And come to define loads, apply, structural, displacement. And the first thing I want to do is to define the symmetries on these two lines. So come to symmetry boundary condition and pick width area. Pick this line first, click OK, and the area is going to be that one. Apply. And I'm picking this line, OK, and this area, apply. So these two lines are having symmetry on them, so that whatever is on the right side is going to be copied on the left side, and whatever is on the top of this line is going to be copied on the bottom of this line. Then I'm going to define a pressure on line of minus 1000 to make that one a tensile sort of loading. Okay. Everything is ready except for I have to define the range of frequencies that I want to apply to this analysis. So I come to analysis type, or I come to load step ops, select time/frequency, and click frequency and substeps. Let's say we want to go from harmonic frequency range of 0 to 50. The greater this number, the longer the analysis will take. And let's say I want to divide that by 100 substeps, and this is going to be stepped. So basically, when you pick stepped, each of these frequencies are going to have the load of 1000 newtons, while if I pick ramped, it's going to start from 0 and reach to 1000 at the frequency of 50. But since I want to have I want to have the load of 1000 or the pressure of 1000 Newton millimeters on each and every of these frequencies, I pick stepped. I click OK. So things are ready. Come to solution, solve current LS, or something I forgot to define. I'm sure it's gonna give me an error. Is do I have to give the density of this material? The reason is for harmonic calculations, the density is also required as to calculate the mass of the model. So I give the density, get back to solution, and click current LS, and I have to wait for a little while so that the solution will be done. So yep, after a while solution is done. Then I can come, well, plot elements, so everything is here. I want to zoom to this point, so I come to here and click zoom and pick zoom at that region. Come to time, history, post-process, and click add data, degree of freedom, displacement in X direction I want to pick, and click OK. It wants me to pick the node. I'm going to pick this node and click OK. Now let's see how it behaves. So for the frequencies of 0 to 50, this is how the that point, the point that I picked, is moving in the X direction, so it's not linear. But if I pick list data, you will also see that there is a phase defined next to the amplitude. Okay. So because so then you can also click this one and add more variables that if you want for your analysis. Let's say we want to see stress intensity. Click OK. Then I have to pick the node again, so I'm going to come and plot elements. Pick this node, OK, and graph that one. So let's see what frequency is that. The phase is 0, so everything is positive. While when I came here and I drew the UX and I click this one, the phase is 150, which means I have negative values, so these values should be negative. How I find that one out is I will explain later, but before that let me show you something else. If you come to plot controls, style, graph, and you come to modify axis, you can change how this graph looks like. For example, for x-axis you can say frequency, and for y-axis you can say UX, and click OK. So if I do that and come to plot and replot, you will see that this changes. You can also come and come to styles and graphs and modify axis. For example, let's say you want to have logarithmic, which doesn't apply really here, but let's just try it and replot everything. This is how, if y-axis is logarithmic, you will see that. The other thing I wanted to show is, let's say we have, I want to plot the elements. I just want to select nodes here. Let's see the nodal solution in x direction for that particular node. Did I pick the wrong one? Nope. Oh, I have to read results first, so I come to, let's say, last set, come back to here, list results for that node, and pick this one again. You see that the UX is negative. That's what I was saying, that when we saw positive values for UX and phase of 180, that means that there's a negative sign in here. We can do this for all sets. Let's say for frequency of, let me close this window, frequency of 20. Okay, we can come and list results and nodal solution, click OK, and see the value is different but still negative. The other thing in fracture mechanics that you may want to study is the stress intensity factor. Let me first select everything. For that one, you need to define a local coordinate system. So I come to here, create local coordinate system by 3 nodes. I pick these 3 nodes. So, and I'm gonna click or stay with number 11. So this is my x and this is my y. The origin is at the crack tip. Then I want to define, I want to come to change active coordinate system to specific coordinate system and pick 11, click OK, go to nodal calculations, or first I have to define a path, and I come to path by nodes and I have to pick 3 nodes for stress intensity factor. I click OK. So these are the nodes that are at the very center of this circle and very end. I click OK. Let's give a name to that, and we can change these values, but I'm going to stick with the defaults and come to nodal calcs, stress intensity factor, click plane strain, and OK. So at this frequency I have a very high mode 1 stress intensity factor, which again, if you take fracture mechanics, you will learn what K1, K2, and K3 mean. But because I had a tensile loading, I only have mode 1 stress intensity factor. I can do this for all the other sets of frequencies that you can try and read different results and get them from there. And with that, I'm going to conclude lesson 20.